As described in the previous unit, the risk ratio RR can be estimated from the sample table of a cohort study. In this unit, we will introduce the population odds ratio, which can be estimated from both kinds of studies. Suppose that in 100 live births, there are 51 boys and 49 girls. Then the odds for boy is the ratio of 51 to 49 or 1.04, meaning a live birth is slightly more likely to be a boy. If an event is very likely, the numerator is much larger than the denominator, so its odds are large. If it is very unlikely, then its odds are very close to zero. Let us apply the concept of odds on the diabetes population introduced in the previous chapter. The odds of diabetes among females is 72,000 divided by 144,000, and that is 0.50. Similarly, the odds of diabetes among males is 52,000 divided by 156,000, and that is approximately 0.33. Thus, males have lower odds than females. The odds for an event is determined from its risk via this formula. For example, the risk of diabetes amongst females is 0.33. Applying the formula gives 0.5. The formula relating odds to risk tells us two things. First, the value of odds is always larger than the risk. This is because the risk is divided by 1 minus risk, which is less than 1. Second, if the risk is very small, then the odds has a similar value. We introduced the odds ratio, more specifically, the odds ratio for an event between one group to another group. In the diabetes population, the odds for diabetes are 0.5 and 0.33 respectively among the females and the males. So the OR works out to be 1.50. Note that this does not mean that the female's risk is 1.5 times higher than the male's risk, since odds is different from risk. In fact, if someone just tells us that the OR is 1.5, we will not be able to calculate the RR without additional information. This interprets the OR in terms of risk. If the OR for a disease between two groups has value 1, then the odds are equal, the risks are equal, so RR is also equal to 1. This is the only situation where a definite RR value can be deduced from a given OR value. So far, odds and the odds ratio are population-level quantities. Now, we turn to the issue of estimating these quantities from the cohort study. The sample odds among females is 378 divided by 702, and that's approximately 0.54, which is quite close to the population odds of 0.50. Similarly, the sample odds among males is 53 divided by 155, or approximately 0.34, which is also quite close to the population odds of 0.33. Hence, the sample OR for diabetes between the females and males is 0.54 divided by 0.34, or approximately 1.57. This is very close to the population OR 1.50. So just like the RR, the OR can be estimated accurately from a cohort study. Next, we'll look at the case control study presented before. We have seen in the previous unit that the population risk for females and for males cannot be accurately estimated from the sample. Not surprisingly, the same holds for odds. Going through the same mechanics, 364 divided by 142 is an approximate 2.56. And this is very different from 0.5, which are the population female odds. 256 divided by 158 is also approximately 1.62, and this is very different from 0.33, which are the population male odds. However, if we continue on the seemingly hopeless path, we get 2.56 divided by 1.62, and that's approximately 1.58. This is remarkably close to the population OR 1.50. So unlike the population RR, the population OR can be estimated accurately from a case control study, provided enough subjects were chosen. The detailed reason is once again beyond the scope here. Very briefly, the errors in the two numbers 2.56 and 1.62 cancel each other out when taking ratio. There is a simple way to calculate the estimated OR, and this is called the cross-product ratio. The table on the left is from the cohort study. As indicated by the arrows, we take the product of 378 and 155, then divide this by the product of 702 and 53 to get 1.57. The table on the right is from the case control study, and this works the same way to give 1.58. In fact, this method works for the whole population as well. The most important thing is to note that the table must be set up correctly. The event of interest should be in the first column, the first group should be in the first row. Then, the cross-product ratio will either give an estimated or the population OR for the event between the first and second groups. It is crucial to identify the study design to collect data, so that an appropriate measure, either a risk ratio or an odds ratio, can be used to investigate association. Population RR can only be accurately estimated from the sample table of a cohort study, but not from a case control study in general. Population OR can be estimated accurately from both kinds of studies. In a cohort study, all subjects by design are disease-free at the beginning of the study. We segregate the subjects by exposure groups. Therefore, what needs to be compared at the endpoint of the study would be the odds of developing the disease between the two exposure groups if we apply odds ratio to a cohort study. So far, we have presented calculations and interpretations of odds ratio when the data are organized in a 2x2 table. What if we have 3 or more levels of exposure and disease statuses? Can we then meaningfully apply odds ratio? This issue is also similar for the risk ratio. Let's look at the study on the relationship between optimism and cardiovascular health, or CVH, treating optimism as exposure and CVH as disease. We see that optimism has 4 levels: low, mid-low, mid-high, and high. And CVH has 3 levels: poor, intermediate, and ideal. The essential idea is to select a 2x2 table out of the 4x3 table according to a question of interest. For example, what is the odds ratio for ideal CVH between high and low optimism? Thus, the low optimism group is the baseline exposure group. The remaining task is to choose a baseline disease group to compare with the ideal CVH. We will choose poor CVH. Then, the 4 highlighted numbers form the appropriate 2x2 table. Using the cross-product formula, the odds ratio for ideal CVH between high and low optimism is 1.77. This confirms our expectation that the high optimism group has a lower risk of heart problems. 1.77 is a good estimate of the population OR, provided random samples were taken from the exposure groups, a cohort study, or from the disease groups, a case control study. Even then, this is an observational study, so on its own, it is not definitive proof that optimism causes better heart health. Unlike the 2x2 case, where it is often clear which groups are the baseline, in larger tables, it is important to state these groups clearly. In this unit, we have discussed the following. In the cohort study, we compared the risk of outcomes between 2 exposure levels by taking the ratio of the risk to obtain a risk ratio. This measure is easily understood. However, it is not workable for a case control study. Generally, in a case control design, the sample table cannot give accurate estimate of the population RR. The exception being the case when the same fractions have been sampled from the disease groups. But the population OR can be estimated. Though OR measures the association between exposure and disease in an unfamiliar way, it is widely used in medical studies. We also extend the odds ratio to a multi-level contingency table. Regardless of whether the data come from a cohort or a case control design, it is an observational study. We need to keep in mind that association does not imply causation.